Welcome all. Myself Sumantana, a synthetic organic chemist, a pretty simple one. And here I have put some effort for discussing a few modern synthetic technologies so that it can help us to know more about the recent trends in organic chemistry. Further, it may be helpful for the upcoming researchers who are about to join the PhD so that they can get some idea about the research topics which is taking place in 21st century. So today I'll be talking about a bimetallic catalysis, and this is basically a nickel aluminum based bimetallic catalysis. The work was done by Professor Tiao Gan Ong group, and it was published in 2010 in the Journal of American Chemical Society. And the work is entitled as Bimetallic Nickel Aluminum Mediated Para-Selective Alkylation of Pyridine. Organic chemistry deals with a number of functionalized organic molecules, and thus the development of new strategies for the incorporation of functional groups in a molecule is always been a point of interest. These are commonly performed as a functional group interconversion processes where a already existing functional group can be converted to another one. However, recent trends in organic synthesis have seen a paradigm shift from the conventional approaches, and now carbon-hydrogen bonds can be used as a synthetic handle for the functionalization. These are obviously advantageous because carbon-hydrogen bonds are pretty abundant in organic molecules, and we do not need any pre-functionalized precursor for the incorporation of new functional group. Further, this generates less amount of waste compared to the conventional approaches. These carbon-hydrogen bonds can be divided into two categories. First is acidic carbon-hydrogen bonds, which are reactive and can be functionalized easily in presence of any base or Lewis acid mediated processes. While there are also some non-acidic carbon-hydrogen bonds in the molecule which has higher pKa value and they are inert in nature, and the functionalization of these carbon-hydrogen bonds are pretty difficult. This term carbon-hydrogen bond activation is related to the latter one. In carbon-hydrogen bond activation reactions, we need a transition metal catalyst which generally interacts with the carbon-hydrogen bond to form a carbometallic intermediate. This carbometallic intermediate is very reactive and can be transformed into various functional groups. Although it looks simple, this has some inherent challenges. First is the polarity of carbon-hydrogen bonds. As I have told, these are quite non-polar in nature. There is almost no interaction with the polar transition metal catalyst, and thus it is difficult to activate such bonds. Further, the number of carbon-hydrogen bonds in organic molecule leads to regioselectivity issues. These issues can be addressed utilizing the conventional enzyme catalysis. In enzyme catalysis, first the substrate comes and binds to the particular site of enzyme and then undergoes some transformation, and after the transformation it can come out of the system and gives us the product. Similarly, if we can incorporate a new coordinating site in the molecule, this coordinating site, which is termed as directing group, can first coordinate to the transition metal. Now this transition metal can interact with the proximal CH bond present in the molecule and thus selectively form a carbometallic species. So we can avoid the regioselectivity issue, as well as the coordination can increase the interaction between the transition metal and the carbon-hydrogen bond. Over the years, various directing groups have been developed, and here I have shown some of them. That may be a bi-coordinating system or mono-coordinating system. You can use the pyridine group or a weakly coordinating carbonyl as a coordinating functionality. So today I will be talking about pyridine functionalization. Devising new strategies towards the functionalization of pyridine is pretty important because it is one of the most abundant heterocycle present in biomolecules and natural products. Generally, if we go a directing group tree approach for pyridine functionalization, we can get three types of products. Either it may be 2 functionalization, 3 functionalization or 4 functionalization. Also, we know that pyridine is a very good coordinating ligand, and if we go through a transition metal catalyzed approach, This pyridyl nitrogen can coordinate to the transition metal catalyst and can deactivate the catalyst. Thus, it is always very challenging to selectively functionalize pyridine in particular position. This can be addressed following a cooperative catalytic process. So, compared to 3 positions, 2 and 4 positions of pyridine are pretty reactive, and if we target for a 4 functionalization of pyridine, we have to go for an approach which can hinder the 2 functionalization. Now, if we add an additional catalyst in the reaction medium, the pyridyl nitrogen can compete towards coordination, and if the additional catalyst, which I have shown as a cat, has a better coordinating nature, so the pyridine will first coordinate to this particular catalyst, and thus the original transition metal catalyst remain effective, and thus we can control the transition metal catalysis. Further, if we look at the nature of these two catalysts, if we can tune the steric and electronic bulk in these two particular transition metal catalyst and the additional catalyst, we can easily tune the selectivity from 2 to 4 position, which I will discuss following. The choice of additional catalyst is pretty important. These are generally Lewis acidic catalyst, and as you know, that pyridine is a very good Lewis base. Further, and that additional catalyst should not affect the original catalyst activity, and that should be sterically and electronically controllable, so that we can control the regioselectivity. So in this case, they have attempted a hydroarylation of alkynes, and so that they can selectively get 4 functionalization of pyridine. Now what they have chosen an Lewis acidic complex of aluminium first, and in presence of a NHC, which has provided 83% yield of the desired product. And this reaction generally goes through a nickel 0 nickel 2 catalytic system, which I will discuss later. So the Lewis acidic catalyst, aluminium, is working well. However, zinc or boron based Lewis acids are ineffective, and the presence of these butyl and mesityle groups are necessary to control the regioselectivity, because you know these are very bulky groups, and thus always it has a steric hindrance with the proximal site, so that you can control the functionalization process. And the NHC is necessary to stabilize the metal center and control the regioselectivity, as I have already mentioned. So with this condition, they have attained a decent substrate scope, and that functionalization of substituted and unsubstituted pyridines are possible with precisely high selectivity. In certain cases like 3,5-dimethylpyridine or 2-phenylpyridine, the selectivity as well as yield is less. However, overall, this process has showcased that it is indeed possible to selectively functionalize the C4 position of pyridine, and also this is viable tool for the functionalization of quinolines 4 position with 10:1 selectivity. Now we have to look at the mechanism of this process. So they have performed a stoichiometric experiment using the NHC, aluminum trimethyl reagent, and a nickel cord, so in presence of pyridine, and they have found the formation of this particular complex, which I have shown here. So they have found in the crystal structure that pyridyl nitrogen is coordinated to the trimethyl aluminum, and the NHCs are coordinating to the nickel 0. So nickel 0, whatever COD, that is cyclooctadiene ligand, is displaced by the strongly coordinating NHC, and it is stabilizing the nickel 0 system. Also, this nickel catalyst is coordinating to the pi bond in between 3 and 4 positions of pyridine, and that is there is a very good pi coordination taking place. Further, when they change the Lewis acids to trimethyl aluminum to chlorodimethyl aluminum, they have found only 29% of desired product formation, whereas the stoichiometric experiment showcased that this aluminum complex formation, and in this cation pair that aluminum dimethyl is coordinated to the carbene, and another AlCl4 minus is also forming in this process. Now if we look at the mechanism, this is going controlled by a SAP principle, because compared to nickel 0, aluminum trimethyl reagent is much more harder, and thus the hard center of pyridine is coordinating to the hard aluminum trimethyl reagent. Nickel 0 is soft in nature, and it is obviously coordinated by the soft NHCs, and also this nickel 0 is coordinating to the activated pi system of pyridine. Following this, now we can discuss the mechanism. So NHC will coordinate to the nickel 0 to form a NHC nickel 0 complex, and now that NHC trimethyl aluminum reagent can be reacted with the pyridine. So that NHC is displaced from the aluminum, and the pyridine can come in place of that NHC ligand, and when the displaced NHC come and coordinate to nickel 0 system. Now this pi coordinated nickel 0 is pretty reactive, and it can react with the CH bond in the 4th position oxidatively. So oxidative addition to the carbon hydrogen bonds with the nickel 0 can give us a nickel hydride system, and to fulfill the coordinating number, that alkyne now comes and coordinate to the nickel 2 system. So this particular intermediate now can undergo migratory insertion. As we know that hydride migration is much more facile compared to the aryl migration. So the hydride migrates to the alkyne to form intermediate 7, and intermediate 7 can readily undergo reductive elimination to give the product and nickel 0 catalyst back. And in the meantime, we can also get NHC trimethyl aluminum reagent back. So both we can use in catalytic amount, and this catalytic system is susceptible for selective C4 functionalization of pyridine. Finally, I'd like to thank you all for watching the video, and obviously you can contact me through email, and this is I have shown here. Thank you.